In this video, I want to talk about the idea of quantifiers. And quantifiers are words that give you information about how many objects satisfy a certain property, and that property is usually expressed as an open sentence. And furthermore, when you quantify an open sentence, remember open sentences are true statements for various values in the domain and false for other values in the domain. Adding a quantifier at the start turns the whole thing into a statement itself, which just has a value of true or false. So working towards an example of one of these, let me introduce our first quantifier. First quantifier is called a universal quantifier. And you can think the universe is huge, it's everything that we know. So this universal quantifier, we're thinking of the words like for all, or maybe any, or each, or every, or words of that type saying everything in a certain domain. So in logical formulas, we usually use this upside down capital A to denote for all. So here's an example here. For all x, we have this open sentence, p of x. Let me make this into a little more of an example by putting some actual open sentences here. So let's say that p of x, where, and let me give this a domain, let's say x is indeed an integer. So let's say p of x is the statement, let's say x is even. So we know even integers, so if x was, say, 0 or 2 or 4 or 6 or 8 or -2 or -4 or -6 or -8 or whatever, then p of x would be true. So if you had something like p of, let's say, 6, so it would be 6 is even. If we had 6 in there, it would be a true statement. But if we had, say, instead of 6, what if we had 7? Well, now p of 7 is 7 even? 7 is not even. So p of 6 is true, but p of 7 is even. That's false. So we know that this is true and false for various elements of our domain, okay? But what if I said this? I said, for all integers x, so for all x that are in the set of integers, for all integers, we have that x is even. Well, if I told you that, well, let's see if you can determine whether this is true or false, or it depends. If somebody said all integers are even, would this be a true statement, a false statement, or would it still be an open sentence where it depends? Well, now that we thought about it, well, if somebody said all integers are even, you'd probably say that's false. Of course, 1 is not even, 3 is not even, -1 is not even. So we've turned this open sentence, x is even, into a statement by saying how many objects it applied to. So here we said all. So for all x, x is even. That's false. Okay. For a lot of times, if the domain is obvious, we don't really state it. But if the domain isn't obvious, if we want to make sure that people know what domain we're talking about, we do like we did just up here. We write for all x in whatever domain set we want. The other type of quantifier that we deal with is something called an existential quantifier. And in the word existential, you see this word exists. Exist. So you can think of an existential quantifier talking about one object, one or more objects. And we write that in logical terms using this backwards E. So that in logic means there exists. So let's do a similar example. We'll keep the same P of X here. X is even. Well, what if I said instead, well, let me do this in black actually. There we go. There exists an integer X such that X is even. Remember, we defined that P of X here, up here. This just means X is even. Is this true? If somebody said there is an integer that is even, well, you'd say that's absolutely true. There's loads of them. There's infinitely many. So this is a true statement now. So that's the idea of quantifiers, of these universal and existential quantifiers. Again, they take open sentences and in some sense convert them into statements by telling you how many objects the open sentence applies to. And just like before, if we need to indicate the domain to be precise, we can do that just like we did here. Let's do the following example. Let's try and go the other way. Let's take this logical formula involving a quantifier and let's write that in English. So pause the video now and give that a go. Okay, now that you're back, well, I will say, of course, for translating things into English, there might be different ways of doing it. Of course, people might have slightly different things, but the main idea will be the same thing. We know that this is indeed a universal quantifier, so we can use a word like all, or each, or any, or every. So this means for all, and this is, well, integers. For all z, where z is in this set, and that's the set of integers. So maybe a good thing to say first would be for all integers, z. We have z over 2, and I'm thinking about this, by the way. I'm thinking about this as a division sign, so z divided by 2. What is this? Well, that is, it's not in the set. That, really, any symbol that has a cross through it means it's not that. So this means that z over 2, z divided by 2, is not in the set of integers, is not an integer. So let's put that all together. So one way you could do it would be for all integers z, well, z over 2 is not an integer. There's an example of a way of writing this logical formula in words. And of course, a natural question would be, is this now a true statement or a false statement? Well, pause the video, see if you can figure it out. And now that you're back, you can see, well, if I put, say, z equals 2 in here, so let's call this P of x. Well, P of 2, well, that's 2 over 2, and that is indeed 1, and 1 is an integer. So this is false. We found an integer where that if you divide it by 2, you get an integer. So we proved this bit wrong. The open sentence is wrong here. So this is a false statement.